Thank you. So, let's see what I can talk about. Well, first of all, a bit about myself. I don't know if you know me. I'm Marc Lemburg. I've been doing Python for quite a long time. I started very early. I have a company doing a Python project for customers. I'm a senior architect for Python and do consulting training. I'm also a Python core developer. I am board member of the PSF and board member of the EPS. And I'm based in Düsseldorf in Germany. So I thought I'd put together a talk with some Python idioms that might be useful for you. This talk is basically focused on people that have just started programming Python and have all these nice things, these nice tools out there and nice ways of doing things in Python, but sometimes don't really know which of the possibilities there are they should use in their code and maybe want to get some guidance in writing better code. So unfortunately, this is the only photograph I have in the slides. Most of the other stuff is just text. There's lots of text on the slides. I'm not going to read everything for you. You don't have to read everything. I'm going to put the slides up afterwards, and then you can download it if you want to get more information from it. So this is the agenda. Quite a few bullets there, so let's start so I can finish on time. So first thing, coding conventions. Of course, you want to know how to actually write your code. And fortunately, in Python, we have a standard for this. It's the PEP8 standard. You can download it on the python.org website. It has evolved a lot over the years. It's constantly being updated to address new questions that you might have. It's written in a way that allows you to write readable code. That's one of I think one of the best features in Python that you have, it's very easy to write readable code. It's a guideline. It's not necessarily fixed in any way. You can change things in there if you want to. You can build your corporate coding guidelines based on it. There's some help from a package called PEP8 that you can run to actually check your code against these PEP8 guidelines. And then it'll point out various things that you've done wrong. You might want to change them. So that's one thing that you should definitely have a look at. One thing that's not mentioned in that PEP8 is the typical layout of a Python module. And I've seen really, well, not very well-structured code in Python modules being written by programmers. So the standard module layout that we usually use in the standard library, for example, or we use in our code that we write, is this one. It's very basic. You have a header, you have a tools section, and then you have a body section. I'm just going to go through this very quickly. It always starts with a doc string. So you put the documentation for your module, what the module does on a very high level into the doc string. Then you start with the imports. I usually put the Python imports first, and then the third-party imports as second list, and then I have the application modules as third list. So it's very easy to see where various things come from in your code. Then the next section is constants. I always put them into one section at the top, so I can immediately see them. And then I have globals, of course, sometimes at least that I need in the module, and put them behind the constants so that you can immediately find them if you need them. Next section then is the tools section. This is basically used for things that you mostly only need in your module. Like, there's one exception here, which is the exceptions section, because sometimes these exceptions, of course, they wander outside your module, and then you want to be able to see where they're coming from. So first, you define all the exceptions that you have in your module, and then you define the helper functions. Defining exceptions, by the way, is very easy. You can just subclass the ones that you have in Python, and then you can have specific exceptions for your module, which is helpful, especially when debugging, because you immediately know which module your exception is coming from. Then in the body section, which is basically the meat of the module, you first define the functions, and then you define the classes, and at the very end, you always have this typical if name equals main, then execute some main function, for example, the module execution part. This is run when you import the module. And it's only run because you have this condition here. It's only run when you import the module at the main scope. So when you write Python and then module.py, then this part is run. You should normally try to avoid having executable code at module scope level so that you don't have any side effects when importing it. Sometimes that's not possible, but you should try to do that. So this is the overview. The red parts here are basically defining your module API, and that's how you can structure your modules if you want to have a really clear kind of approach to it. Then, of course, it's like everything in Python, you should always use descriptive names for your modules. It should be more or less immediately obvious what the module does. There's a typical way of doing that in Python. You usually take the most important class, for example, that you define in a module, and you name the module after that class. I already told you about the executable code, and one recommendation I have for you, you should always use absolute imports. If you have packages, then you can also use relative imports, but if you have larger projects, then absolute imports make your life a lot easier, so you should just avoid the relative imports. So now I'm going to start a tour from high level to low level Python idioms. It's just a collection of things I put together. I don't have enough time to go into all the various details. I could probably talk for a few hours mentioning everything, so I'm just going to skim a few things. I'm going to give you pointers for other things that you can look at. The first thing I want to start with is common patterns that you have in Python. How many of you know coding patterns, like the Gamma book, for example? Not that many people. So software patterns are basically things that people have become aware of, common things that you do again and again when programming things. So there was the Gang of Four, I don't know how many years ago, many years ago anyway. They wrote a book called the Gamma book, and that basically lists a lot of common patterns that you find in software design. And these are some patterns that you have in Python. Some of them are not mentioned in that Gamma book. The most famous pattern in Python, of course, is the duck typing pattern. So in Python, everything happens using duck typing. You're always interested in your API. You're not so much interested in which base class some object is derived from. So the principle behind duck typing is if it looks like a duck, if it quacks like a duck, then it's probably a duck, and that's good enough for Python. So it's not like in Java or statically typed languages where you actually have to make sure that a certain base class is being used. And there are lots of examples of that in the Python standard library. The next one is the facade or the adapter pattern. This is used in conjunction with the duck typing pattern. You try to make an object that you have look like another object. So basically, you make for example, some bird, make a bird look like a duck so that you can use it in your code that uses the duck interface. This is the facade or the adapter code. And again, there are many examples of that in Python. Then we have singletons. You probably know false and true. None is also a singleton. Ellipsis is a singleton. We have a special singleton called not implemented. You probably don't know that the small integers in CPython are singletons, so they only exist once in your process. The next one is factories. So in Python, you only have a single init, dunder init method to create objects from classes, and sometimes you want different ways of creating your objects. And before we had class methods in Python, the only way to do that was defining a function, just a regular function, which then returned an instance of that class. And nowadays, this is not recommended anymore. Nowadays, you should use class methods for this. So this is just a way of having multiple init methods, basically. Multiple ways of defining or initializing your objects. The next pattern is wrappers or proxies. This is, again, similar to the facade or adapter. In these cases, you try to hide certain things from other objects, or you try to add certain information to objects. It's very commonly used in, for example, in decorators. When doing this in decorators, you should watch out that you don't create too many wrappers, because then your tracebacks look very ugly. You can see that, for example, if you're using Django and you have a bug in your Django code, you sometimes get tracebacks that span multiple pages, which is not very nice. And most of those, the listings that you have in there are because of these wrappers, and they don't really interest you. So you should not really, well, wrap stuff if you don't really have to. And finally, we have callbacks. Callback pattern is a very standard pattern that you use in asynchronous processing, for example. You can also use it in synchronous processing, for example, when writing parsers. So in general, whenever some event occurs, you register a handler for that event, and that handler is called a callback. And this callback is then called whenever this event happens. So for example, if a parser hits a certain element type, then a certain method is called, and you can do something. And what's very popular in Python, because it's all dynamic, you can dynamically also introspect your classes for these handlers. So you can dynamically create handlers that interact with your parsing. This is very difficult to do in other languages. And then finally, there is something I want to put some emphasis on. This is not really a coding pattern, it's a code evolution pattern. It's a way that you start writing Python code. So what you typically do is you have just a simple script, just a few statements that you put into a .py file and you execute them. Then you find that you need to make it a bit more complex, maybe add more features, make it look a little nicer. Then you take the sections that you have in there, you turn them into functions. So the functions is the next kind of evolutional step that you have in your script. Then you group the functions, and then you can make use of the feature of the object-oriented feature that we have in Python, that you can put everything into classes, and you refactor your functions that you've just created and put them as methods into classes. And then you can instantiate your classes, you can run your application like that. You can make it even more feature-rich, you can add more customizations. And once you do that, you can start doing subclassing to, for example, adapt certain features, have multiple features be more or less the same, except for maybe one or two certain details. You don't have to repeat yourself all the time. And then you can put everything together in loosely coupled components, which are basically sets of classes, and tie your whole application together like that and grow really big applications like that. I have a completely separate talk about this, so I'm not going to go into details here. But I just want to recommend, when you start writing code, don't necessarily start with writing code just with classes, for example. Start easy and then get more complex and have your code evolve like that. It's a much better way to evolve your code, because then you learn about what you actually need in the code, and it's not so much about just putting everything into classes and making everything complicated right from the start. So, next thing, performance idioms. Again, I have a complete separate talk for this one, so I'm just going to mention a few things that are interesting. One thing is looping over sequences. You always have to do that in Python code. There are various methods of doing that. One is the for loop, then you have the map function. You have list comprehensions, and you have generators. And I sat down and timed everything, and I found that the simple answer is use list comprehensions all the time. It's the fastest way of doing this. So if you remember anything from this talk, this is a good one to remember. Then the next one is joining strings. The obvious way of joining strings is just using the plus, so the concat operator on strings. This is good when just having a few strings, and it's good for readability because it's nice to read. The other way of doing this is using the join method on strings. So you pass in as parameter a list, or any iterable, basically. The argument, the object that you're iterating, you're calling the join method on, is the separator that you want to put into your list. And then it'll do the joining for you. And this is great for if you have multiple, if you have many strings. And all the other methods of doing this that are floating around a mailing list and use groups are not really better than any of these two. They're usually slower, they look ugly, and you should try to avoid them. Something else, exceptions. If you write code that uses exceptions a lot, you should be careful that you write the code and structure the code in a way that you put the code that runs more often or is more likely to run often into your between the try and except. So if you put code that runs very often or more often than the common case into the exception part of that try except, then you'll find that you'll have a huge slowdown in your code. This is because it's very expensive to raise Python exceptions. It's not expensive to do that at C level, but if you do it in Python, it's expensive. And so you should only use the exceptions for exceptional cases. If you get this wrong, you can have a slowdown of 10 times sometimes because of this. So that's why I'm mentioning this. And then if you want to have more of these kinds of performance hints, then please have a look at this wiki page, or you can download another talk I gave, When Performance Matters, which has a lot more of these details. So let's have a look at some coding idioms. Something that I sometimes see in other code, in third-party code, and that I look at, or code from other programmers I work with, is that they start to nest if statements very deeply. And you get this kind of syndrome, what I call a staircase syndrome. So your if statements, they tend to move to the right all the time. And that's a very simple way of avoiding this. Of course, this doesn't look good. It's hard to read because you cannot really follow the indentation anymore. Fortunately, you have the continue statement in Python, which makes it very easy to avoid this whole thing. So you just restructure your code a bit, and then you use continue to just switch to the next loop in your for statement. And so you don't need the indentation anymore. You can just avoid it, and everything becomes much more readable. The same is also possible with functions, except in functions you would use the return statement and not the continue statement. Right. The next thing to watch out for is mutability or immutability. Because in Python everything is, or pretty much everything is mutable, you can use mutable things in places where it's not a good idea to actually do so. For example, if you put mutable things into the module scope, for example, a database connection, then this may look very natural to you, this may look nice from a writing perspective, but it's not thread safe. So if you have multiple threads running, accessing that same connection, it will definitely give you problems sooner or later in your application. And especially if you use larger applications or you write larger projects, then you should not do this. Instead, what you can do is you can have context objects, and you create these objects. They have all the context that's needed for example, for a web request or an RPC request. You put the information in there, and you pass around that object, and that object would then, for example, in the database case, would then also have the database connection. And you pass it around as first parameter of your functions, or if you're using classes, you put it into a class instance attribute and do it like that, and then you avoid these issues, and everything keeps working. The same thing can happen when you define default parameters in functions. So for example, down here you have func and then a equals none. What you really want for that default parameter is you want a to be an empty list when it's not being passed in as parameter. Now, if you'd use an empty list instead of the none here, and then your function starts doing something with the a parameter here, it would the changes that you make to that list would persist, and so all the future function calls to the function func would then see those changes that you've made. And of course, you don't want that. So the best way to avoid this is if you have to put something mutable as default parameter, replace it with none, and then in your function, use the mutable parameter that you need as default and put it into your variable inside the function. A similar case is for class default attributes. So if you have define a class, you have attributes. You want to say, for example, maybe files is supposed to be a list of something. Then you'd normally write files equals an empty list. You have the same problem again. Some method in your class may change this list, for example, in some method. And then the change would be on the class object. And so all your instances would see those changes. And you don't want that. So what you do is you place the assignment for that instance attribute into your init method to avoid this. So some gotchas. How many of you know the in operator in Python? All hands should go up, really? Yeah. So, I mean, the in operator is used for membership testing. So if you want to check whether something is in a list, you should definitely use the in operator. You should not use the index method that you have on the list. This may be a bit unusual for you if you're coming from other languages, which always use methods for doing these things. It's better to do it that way. For dictionaries, it's not necessarily obvious what x in some dict would mean. In Python, it means that x, the key, is in your dictionary. So if you test with this, it's the same as the .hasKey method. And hasKey is deprecated anyway, so you should only use this one. For sets, sets were added very late in the language, so sets don't even have a method to do this in operation, so you always have to use this, which is good. So you cannot make any mistakes. And some more gotchas. If you do Boolean testing in Python, then you have, of course, you have true and false, the two singletons I mentioned. There are various ways of testing for Boolean, for truth or false. One way I often see is people writing if x equals true. It's not a good way to do this because it may fail. True actually is an integer and it has the value 1. So if x, for example, is 2, then it's still true, but this won't work. So your print statement wouldn't execute. And even more so if you write x, if x is true, because is actually checks the address of the object. And of course, unless x is actually your true singleton, this will never be true and never print x is true. And likewise for the not case. So this is something to remember. And similarly, if you do empty container testing, so you want to check whether a list, for example, is empty or tuple is empty, you should always use if and then container, because empty containers in Python are always false, and containers that have something are always true. So this is much more efficient to do it that way. You don't need the length function for this. You don't need to check whether the length is positive, because length can only be 0 or positive, so that's really not necessary. And finally, something well, it's a mistake I often make. It's the comma in Python. If you look, you have one tuples in Python, so you can have a tuple with one element in it. And the way to write it is you use the parentheses around the 1, and you have to have this comma at the end. Now, this is it's obvious to see that this is a tuple, but the next line is also a one tuple, and this is not obvious to see. And the mistake I sometimes make is I accidentally add the comma to the end of the line, or maybe I do a copy-paste from somewhere, and then the comma just gets added. And as you can see in the example here, I originally wanted to have s equals abc, the string abc, but what happens is it actually creates a one tuple, so the length of s is 1. It's not 3, as I would have expected. And similarly, if I index into s, I don't get the c. If I ask for S2, I get an index error because it's a one tuple and it doesn't have a third element in that index. So this is something to watch out for. But commas are also nice in Python because the Python parser is very nice to you because it allows having commas in places where you normally don't need them and where other languages, for example, give you an error message. So if you have listings with, say, a dictionary with items, you can have the comma at the end of each item, including the last one that you have in your definition. And this is very nice because if you want to add new elements to that listing, you can very easily do so, and you just append a comma and you're done. You don't have to worry about any syntax errors that you might get if the comma is missing. And this even works for functions. So if you have functions that take lots and lots of parameters, you can do it that way as well. So, I'm just going to show a few more tools that you can use. The nice thing in Python is that whenever someone has a problem, they write a tool for it, and they put it on PyPy, and everyone can use it, so we don't have to repeat ourselves all the time. There's a very good tool called PyLint. This is for style and typo checking. It has good documentation. It creates quite a few false positives, but you can configure it to not do. So you should definitely have a look at that. PEP8 already mentioned. PyFlakes is another one. It does logical checking. Unfortunately, it doesn't have much documentation, so you should probably have a look at Flake8, which is kind of the combination of PEP8 and Flakes, and also adds an extra complexity checker. It has good documentation, so you should probably look at this one. And then there is PyChecker, which is a very old tool. It predates all the other tools. It's not maintained anymore, but it can still give you some good results. So now is question time. That was it.
Hi.
Hi.
What idiom would you recommend to check if it is not none? Like, I just need to do some actions if the object is none, but I should not like look for true, false.
I did not really understand your question.
Okay.
Your object is done?
None.
Ah, none. Yeah.
None type.
Because none is a singleton, you should always use if x is none as check. It's the fastest way of doing it because in C it's just a pointer comparison. And it also immediately becomes clear that you're looking for exactly that particular value. So you should not write if x equals none, especially not in Python 3 because that's always going to fail except if x is none. More questions? No? I think we ran out of time. Thank you.
So I'm the next speaker.
All right, nice.